Hello and welcome to EngPhys 3BA3 Lecture 15, Op-Amp Oscillators and Artificial Inductors. Here we're going to be looking at how you make timing circuits for inside of a computer. This is, first we're going to look at this circuit right here. This is called a Relaxation Oscillator circuit. So it's going to have an output that looks like, that at the input looks like this. It's got this kind of shark fin thing. That's kind of neat. And the output looks like this. It's a square wave. Let's see why. Okay, first assume that the capacitor is initially uncharged. And so if this is 0, then let's see what's going on here. We've got this is 0 volts. There's the feedback doesn't quite work right. You know, we've got things going to the positive terminal and to the negative terminal. So let's say that we're not having equal voltage here. So this is just pinned, let's say at positive Vs. Okay, so this is positive Vs and this is 0. Which means voltage divider for here, we've got a positive number, so we've got positive feedback in this situation from that setup. So if this is at the positive number, at positive Vs at the output, then it stays pinned there. Okay, but what happens over here? Well, now we've got 0 volts there, positive Vs there, so current's flowing this way. It doesn't flow into there, flows into the capacitor, which charges it up. So we're charging up the capacitor in time. Eventually, the capacitor charge is going to make the voltage on the capacitor higher than this voltage divider gives. And then what happens is this swings to the other side. So the output swings negative. And now this goes to some negative number, and we've got a negative voltage here, which is going to draw current out of the capacitor to discharge it until eventually the voltage gets lower than this voltage at the voltage divider again when there's a negative voltage here, and then it swings back up, and that's what's going on. So we're constantly discharging, charging, discharging, charging the capacitor. If we start at 0 on the charging cycle, so the place we started on this curve, we said, okay, we're at 0 volts in the on the capacitor, which means 0 volts at the negative input terminal, and a positive output, and that was this situation right here. If we had assumed that we were at 0 volts and a negative output, then that's just this point. We would have started there. We would have found the capacitors initially going to more and more negative voltage. I don't really want to call that discharging because it's charging but in the negative direction now. And then once it gets below that threshold, the output swings up and immediately we start getting more positive voltage on the capacitor with time. So the input therefore does this and the output does that. We explained it qualitatively. Feel free to look over the notes and run the math of this. It's nothing you haven't seen before to calculate what the circuit is actually doing and how you can come up with this numerically. All right, so the critical component of this that you'll come up with is the left part of this equation here. I guess I got the whole thing together up here. So this is telling you the rate of change of the voltage at the negative terminal in terms of what the output voltage is at that moment and what the voltage at the negative input terminal is. So this is a differential equation. At any point, the output is a constant, so you just pick a constant output voltage and you can solve this differential equation and come up with one of these curves. Keeping in mind that as soon as the voltage dips below one of these thresholds that we figured out, then the output of the op-amp switches, and so Vout switches as soon as we change which side of this is more positive or negative. Because of the positive feedback, this is acting like a comparator, so you have to check when we get to that voltage level. This is a way to generate a clock in a computer. So in the digital circuits, we often were using a clock pulse. We needed this kind of square wave that's going between 1 and 0, or positive voltage and negative voltage to run a lot of our digital circuits. Okay. First thing, show that the period of relaxation of this oscillator, period of the relaxation oscillator that is, so the time from one peak to the next peak, is equal to this, 2 RTC ln of this ratio, independent of the value of Vs. Okay? Well, if you're still listening and you didn't give it a shot yet, I'll describe how you can do this. What you should do is go back up to this differential equation, and then for a fixed V out, solve the differential equation. It's a first order differential equation. You used to be able to do this at one point. I think you can still do it. I have faith in you guys. So solve the differential equation. It's linear, no sweat. It's not separable, so you just have to use that integrating factor thing and you can solve that all up. Anyway, then once you've solved the differential equation, give it an initial condition of the voltage being this, Vi minus initially is this, and then solve for the time it takes for it to get down to this bottom point. By symmetry, you can say that it should take the same time to get back up, but if you want, you can resolve the differential equation for the different output voltage, in that case of a positive voltage, and then find out the time that it takes to go back up. And then the total difference in time from that starting time to this time is the period of the relaxation oscillator. Okay, so here's doing just that. What we do is we start with, we say, okay, well, this is the starting voltage, that's our initial condition, solve the differential equation, and there's the solution in terms of V out and what what Vs is. So, well, rather than, this is not V out, this is V initial here. So a little bit confusing. This is not an O, this is a 0. So we were using V out in this picture. Notice the small o, and this is V initial here. So that's just our initial condition when V out is negative Vs. So this is the falling part. We had to put in V out as negative Vs to get this solution. Okay, then substituting in that at t equals 0, we want this to be our voltage. We can come up with what that initial voltage should be, and then we can solve for the time, as described earlier, that it takes for it to get to this negative switching voltage. So t is equal to this, and the charge up time is the same by symmetry, so we end up with 2 times this for the period. And in case you got stuck on the differential equation, here's a reminder of how to do that. So you have the differential equation here. It's first order linear. Put it into standard form, and then find the integrating factor e to the integral of the coefficient of Vi minus, which in this case is e to the t over RTC. Then multiply both sides of the differential equation in standard form by that, and factor the left-hand side into the derivative of Vi minus times the integrating factor. Then integrate both sides, which on the left you can just use the fundamental theorem of calculus to cancel the derivative. On the right-hand side, the integral taking VO as a constant, which it is at any one point, we can just divide by 1 over RTC, and that cancels out that coefficient in front that we had. Now solve for Vi minus by dividing both sides by e to the t over RTC, the integrating factor, and we're left with the constant V0 times e to the negative t by RTC plus V out. So when it's discharging, V out is negative Vs, and voila, we're at this equation that we started with here. Exercise 627, determine the time-dependent voltage behavior of the relaxation oscillator, shown in 614, if the supply voltages instead of positive Vs and negative Vs are positive Vs and ground. So if instead of hooking up this op-amp to plus Vs and negative Vs, we hook it up to plus Vs and 0, then how does this behave? Well, because this is grounded, on the discharging time, once this is 0 and we're sort of running the capacitor in the other direction, then we're going to have a really hard time getting the input voltage here to actually be lower than 0. So unlike before, it's not going to be able to get low enough. It's not really approaching a low enough number to switch. It's like if the switching point became 0, but then 0 also became the point that we're artificially approaching, or rather infinitely approaching, for the discharge of this RC circuit. So we're never actually going to reach that point. Now in practice, if we can get arbitrarily close to it, and then any small oscillation in the voltage will cause the comparator to switch again. But it's not really as reliable of an oscillator in that case. It just sort of spikes up and then takes a reasonable time to decay down. But at any point when it's getting closer and closer to 0, it may spike back up, and that's not going to be as consistent as this sort of oscillator. All right, now this relaxation oscillator notwithstanding, the vast majority of oscillators that you'll actually find in computers are quartz crystals or piezoelectric oscillators. Now, how do these things work? First, we need some information on how piezoelectrics work. You may be familiar already with the idea that if you put a voltage across a piezoelectric, you put an electric field on it in the right orientation, then that causes a deformation of the material. Piezoelectrics are special kinds of crystals that have just the right kind of charge and structure asymmetry, so crystal asymmetry and charge asymmetry, to couple their stress fields to their electric fields, which means that electric fields create deformations in them and vice versa, deformations create electric fields. So if you were to build a capacitor and use a piezoelectric as the dielectric for the capacitor, as the material between the plates, then when you apply a voltage across it, you cause the piezoelectric to move. And like any mechanical structure, it's going to have a mechanical resonance. And if it's moving, it can do work on the area around it. So maybe it's doing work on the air, it's dissipating energy if it's resonating. Well, we just built a capacitor, but then on the other side of it, we've got all this magical behavior. Capacitors can't actually dissipate energy. So electrically, it must actually look like something different than a capacitor. In fact, it does. It looks like, from the electrical perspective, a capacitor in parallel with an RLC branch. And the amazing thing is that it turns out that the energy that you calculate electrically that you're dissipating in this resistor is where the mechanical dissipation energy comes from. The inductor turns out to be proportional to the mass of the thing, and the capacitor turns out to be proportional to its stiffness or mechanical spring constant. Everything works out. Now, if we build this into a circuit, we'll use this symbol. So if you see this in a circuit, that means a quartz crystal. Looks kind of like a capacitor, and that's basically how you build them. You just put plates across this crystal in the right orientation. Now, let's look at how we can make a clock circuit from this. So what we want is to make this a clock circuit like the previous circuit. This is really just labeling VI. We're not actually setting a voltage in here, and we're getting the voltage out here relative to ground, and because of the behavior of the op amp, it doesn't affect drawing a current from here doesn't affect this, but we have to be careful on this side because maybe drawing a current there would affect the rest of this. So we may want to put this into something that has a high input impedance, like another op amp. Okay, or like a flip-flops clock input, something like that. So here's how this works. The op amp, we're hooked up to the inverting terminal, so we're going to get an output here, which is proportional to the negative of the voltage here, except because there's no because we don't actually have the right sort of circuits for feedback, this is just pinned to 0. Whatever voltage here is, if we've got a positive voltage here, then this op amp's behaving more like a comparator, and so we're going to be pinned to negative Vs. If we've got a negative voltage here, we're going to be pinned to positive Vs. So what's going on is the op amp is outputting a square wave of some kind, like the crystal's moving around, and let's presume that it's outputting some kind of a square wave. The square wave is writable as an infinite series of sine waves using the odd frequencies. So you can calculate that if you like, or you can just take my word for it. This is nothing really special. You can use Fourier series terms that you did in second year math to write this out again. Or you can just use the guess and check method. So try and plot this in Maple with enough terms, and you'll see, it gets closer and closer to a square wave. Okay, I can take this as given. Anyway, the next thing that the square wave encounters is this RC forming a low-pass filter here. So the low-pass filter, we tuned this so that when the square wave here is around the resonant frequency, the fundamental resonant frequency of the crystal, then we're only going to be keeping the first term. So we drop the 3, the 5, etc. So we're just looking at driving this with a single frequency sine wave. Okay, now this RLC branch, around the resonance, we're going to neglect the package capacitance here, and we're going to neglect the other resonant mode. So any mechanical structure is going to have multiple resonant frequencies. When you've got like a real solid object there, a single mass on a spring maybe just has one resonant mode, but this any real physical system in 3 dimensions has lots and lots of resonant modes. So we're just going to look at the fundamental mode and neglect all the other RLC branches. So this is just behaving like an RLC, and we've got this capacitor here. This is outputting a sine wave to the input of this, and so we've got that sine wave output, which is a sine wave V0 sine omega t. And then what's the voltage here? So the voltage here, the input to the op amp, is from a voltage divider between this RLC branch, C2, and the input V0. So we've got that VI is the impedance of C2 divided by the impedance of the RLC plus the impedance of C2. This is just a voltage divider on this section. Okay, substituting in the impedances, and then we'll say crystal oscillators have really high quality factors, which means that the R in their RLC branch is quite low. The only time you have to consider it is if you look at just the RLC branch. But because now we've got this other thing in the circuit where we're adding to it, Z of C2, then around the resonance, we don't have to worry about R even. So we're going to drop that as well. And then all the terms have an I. We can divide that out and multiply by the frequency and rewrite everything like this. Then we can substitute in the natural resonant frequency of the RLC branch is root of 1 over LC. So in terms of L is 1 over C omega squared. Substituting that in, we get this as the kind of transfer function to get us from VO here back around to the input. Now the op amp has this op ampy infinite gain to go from here to there, but because we're hooked up to the negative input terminal, it inverts it. And now the crystal has this other term that gets us back to the start, and here's this term here. Well, when is this going to start spontaneously oscillating? That's going to be happening when the Barkhausen criteria are true. These say that there needs to be a net gain in the system. Well, when you're at resonance, so when we're not starting oscillating anymore, but we're holding a resonance, then the gain needs to reduce to 1. And that would be because as you start oscillating bigger and bigger, eventually the R increases. But at least when we're not oscillating and we're going to start oscillating, the R is not that big. And the response interferes constructively with the excitation, which means that it has a phase shift that's a multiple of 2 pi. So what we need is that the response to V out, so the response of this whole system, if you think about like from the crystal here, then going around and going back to the same spot, we need to be an integer multiple of pi by 2 of a phase shift. So either no phase shift or not pi by 2, of 2 pi of a phase shift. No phase shift or 2 pi or 4 pi or 6 pi. Something so that the crests and troughs line up with each other. All right, so since this is an inverting amplifier and we're going to have negative the voltage, so V out is negative when V in is positive and vice versa, to get us back to a system that's amplifying itself, we need this to act like an inverting amplifier as well, right? The RLC dividing with the C2. So to get that to happen, we need this to be a negative number. This is a real number because we had all the i's canceling out, so this just needs to be a negative number, and then we've got one inversion from the op amp and another inversion from this to get us back to the same sign that we started with. Okay, so for this whole thing to be negative, we need it to be less than 0. That means that the denominator needs to be positive. And as long as the frequency is around resonance, then we can just say that omega plus omega naught is basically 2 omega naught. And substituting in and solving, we find that we need the frequency to be bigger than omega naught times 1 plus C over 2 C2. Okay, so we need the frequency to be slightly larger than omega naught for the response to be in phase with the excitation that created it, which means that the thermal excitations in the crystal, which tend to happen biggest around fundamental resonance, are going to be amplified with the system, and so it spontaneously oscillates at nearly the resonant frequency of the crystal. At actually the resonant frequency of the crystal, we don't have the responses in phase with the signals that created them, so those oscillations tend to die out. But at as close to the resonant frequency as possible, so as low as we can get, which would be exactly omega naught times 1 plus C over 2 C2, those signals will be amplified quite a lot by the op amp, and so this just starts spontaneously generating that square wave. The reason that we use quartz crystals rather than this RLC, this RC thing that we had up here, the relaxation oscillator, is mostly because quartz can be cut in a way that gives it a really good temperature stability. So we want our clock to always have the same frequency, whether the computer is at, like you're just turning it on and it's maybe cold in the room, it's at 10 degrees, or it's been running for a while and this part of the board has gotten up to 75 degrees. You don't want that to affect what the output of the frequency is. You don't want the computer to start trying to run faster or something because it's hotter. And certain cuts of quartz have essentially no temperature coefficient to their resonant frequency, so we can make really accurate timing circuits that work over a wide range of temperature. All right, 6.6 active frequency filters. We're not actually going to be talking about filters this section. The first thing we're going to be doing is talking about how we can build inductors, so artificial inductors, without actually using inductors. What's the point? Well, if you wanted a big inductance, you've got to take like an iron core and you've got to wrap a bunch of coil around it, and that's how you make a really big inductor, which is all well and good if you're dealing with big circuit components. But if you want to build like microcontrollers and have really good filters in there, inductors are kind of out of the question. You can't take this big iron rod with a bunch of coil around it and fit that into a microcontroller. Like for capacitors, you just have to make the plates really close together. You don't actually need a huge amount of area, and you can get the capacitance really big. But for inductors, you can't really cheat like that. It's very difficult to build inductors on the small size scale. So for this reason, and the fact that inductors tend to have nonlinearities and large resistive losses, it's better to make artificial inductors if we can get away with it. And here's how we're going to do this. We're going to use a magical circuit element using an op amp that has a way to give us the negative of whatever impedance follows it. If we could make a negative version of a capacitor, then we'd have something that kind of behaves like an inductor, at least at one fixed frequency, where it's got this positive I term. It's proportional to positive I. Okay, so let's look at this thing. How does this work? This thing in the box is called a negative impedance converter. Let's calculate how it works. So we've got we're gonna find out the impedance seen from this perspective. So from the input, what does it look like the impedance of this thing is? Assume that the negative feedback of this is operating, so it's not pinned to any of the outputs. The input current is going to be equal to the input voltage minus VO, not really the output voltage. We're not connecting that to anything. It's the output of the op amp anyway, minus VO over R. Okay, so there's the input current, VI minus VO over R. And the current going down this way is VO minus V plus over R. Okay. And it's also equal to the current through the capacitor. So we'll say that this is VI plus divided by Z of C, impedance of the capacitor. It's the current through that. Okay, so the current through here is this first term that we figured out. It's not equal to the current through there because current can come out of the op amp. But the current through here is equal to the current through there because nothing goes into the op amp. Okay, now if the negative feedback's holding, then VI plus is equal to VI, which is VI minus. So we could calculate what the impedance seen upstream is by taking the rate of change of the input voltage with respect to the input current and substituting in the input current that we found. We've got this equation. So all we've done is just basically divide by this, saying that derivative of, or the rate of change of VI minus VO is just the difference in their rate of changes. So then we can rearrange this equation that we found to solve for what the rate of change of VO is. So since we had this equation, and then we used this equation in our definition, we should substitute this one into it to get rid of VO. So VO written in terms of dVi is this, and then substituting that in and simplifying, you find that actually we've calculated the impedance viewed from upstream of this is negative the impedance of the capacitor, Well, we didn't actually have to say that this was a capacitor. We just called it ZC, Z of whatever that is. So this thing in the box is magically makes the upstream version C an impedance which is negative of whatever came after it. Okay, so let's look at this. How is this circuit going to behave? Well, now we've got a negative impedance converter. So from here we see negative R, and that's in parallel with R and ZC. And so from up here, we'll see negative R in series with negative R in parallel with R in series with C. And that's what we've got here. We've got negative the R in series with 1 over negative R and 1 over R plus ZC. Calculating all that out, we find I omega C R squared. Now this one here, the first simple one, if you just put a capacitor, then you find the output is negative ZC, which would give you an impedance of I over omega C. Okay, that's good. It's close to an inductor. It at least looks like an inductor at one frequency if you set this to be true at the frequency you want and solve for the capacitance you should use. But it doesn't have the right frequency dependence. So an inductor, you expect the impedance to go up if you increase the frequency. But for this one, it would go down. So it still behaves like a capacitor in that respect. It just has the correct sign to be like an inductor. So it would give you the right phase shift direction, but not the right phase shift magnitude. But this circuit does work in the right direction. We've used magic and gotten the frequency to be in the numerator. So now this behaves just like an inductor, as long as C R squared is what you've called L. The entire thing in the dashed box, by the way, is collectively known as a gyrator.